Section 2.5 Measures of Position. Our last section we talked about how to look at data in terms of relative volumes. This time we're going to look at data in terms of its relative position to each other. Again, we are going to sort this data from lowest to highest, and you should know when I do homework or classwork or even on quizzes, I always sort it for you. You're old enough, you don't need to figure out how to sort data, and I'm not going to waste your time with that. So your data will always be sorted. But in the real world, it may not be, so be prepared for that, and that's where we're going to go over Excel in the coming weeks. Microsoft Excel makes life a lot easier. I got a set of data here, and what I've done here is I've sorted from lowest to highest, or I do at 20, 30, 29, 22. When I sort from lowest to highest, and the lowest being 11, the highest being 35. What I'm going to do is first I'm going to find a median, as we learned from before in the previous section. I want to look at this data to see how it's distributed. We talked about our kurtosis before. We talked about skewness. This gives us a good indication with a small group of data of how it's distributed. Now, once I've sorted my data, I found my middle number, which is my median. And this is, we're going to divide it in fourths or quartiles. So the median, which is the 50% mark, the middle number, it's also known as the second quartile, 2 out of 4. And what I've got here, my lowest being 11, my highest being 35. My median, my middle number is 25. And it's simply found there are 7 numbers below it and 7 numbers above it. Now, I also got to find the number between the lowest and the median. So in other words, the number between number 11, which is my lowest, and 25, which is my median. And that is 23. There's 3 below that one and 3 above that one. And that's halfway between the lowest point and the median. That's my first quartile, my 25%. And in my third quartile, I do the same thing. I find what's between the median and the highest number. In this case, between 25 and 35. And this group of data, it's 30. There's 3 below 30 and 3 above 30. That's my third quartile. So now I divide it in groups of 25%. 25% of my data is below 23. 25% of my data is between 23 and 25. 25% of my data is between 25 and 30. And 25% of my data is between 30 and 35. These are quartiles, 1/4 each. When we talk about the interquartile range, that is the distance between my first quartile and my third quartile. And we simply find it by subtracting those two numbers. My third quartile is 30. My first quartile is 23. 30 minus 23 is 7. And that is my IQR, or my interquartile range. It's the middle 50% around the median. Once we found our quartiles, we can develop a simple way to look at how the data is distributed visually with a box and whisker plot. We need to find our lowest entry, which is in this case 11. Our highest entry is 35. And that's why you need to sort this. Our Q2, which is our midpoint, our median, which is 25. Our Q1, which is 23, and our Q3, which is 30. And what we do is we're going to see how the data is distributed. This really gives us a sense of the kurtosis. The lowest entry is put as a dot. You can see it's 11 here. And there's a line drawn to the Q1. The highest entry is also drawn as a dot and a line drawn to the Q3. Between the Q1 and the Q3, remember that's our interquartile range, we have a box. We put, and it has to be basically developed to scale to see how it's distributed. Our Q1 is the left side of the box, our Q3 is the right side of the box. Our Q2 is the median, that's the middle number. And this is called a Box and Whiskers plot, the whiskers being the lowest and highest ends, and then the box being the interquartile range. This lets us know how the data is distributed. Similar to quartiles, we have percentiles. Quartile being 4, percentile being 100. And we simply look at the number of entries to a certain point we're looking at, divide by the total number of entries, and multiply times 100 gives us the percent. You've done this before many times. What percent of this group of 25 unique data points, and again it's sorted, are less than 8? There's 25 points total. There are less than 34 is the digits. Anywhere from 16 to 33 are the unique numbers. And there's 8. The first 8 are less than 34. So, number of data entries, 8 divided by 25, which is 0.32. It's 32%. It's that simple. 8 divided by 25. So 32% of the data is less than 34. Now, there's even deciles, and this is in groups of 10. Again, I've sorted this from lowest to highest, the lowest being 16, the highest being 97. And I want to know what is a decile, which is a tenth, is less than 41. And you can see I've got 50 unique digits here, 50 unique sets of numbers. And I want to know what decile, what group is less than 41. So when I look, my lowest number is 16. I go up to 40 because that's less than 41. And that ends up being the first 15 numbers. 15 numbers, if I count 15, 18, 18, all the way to 40, there's 15 numbers out of 50 total. That is 0.3. 0.3 times 10 is the third decile. So what decile are those less than 41? It'd be the third decile. And you can see I've written here how to look at these deciles. 10% is the first decile, from 10% to 20%, or 0.1, 0.2 is second decile, and so on and so forth. Now, we're going to cover more of this in our next section, next chapter actually, but I want to teach you a basic component we'll be using the rest of the semester called the z-score. Now, let's talk about normal distributions. This is a bell curve. The data under this curve is 100%. All the data. All the data, if we did a sample here, how many would it be? 100%. Now, from -1 deviation to +1 deviation, that is 68%. In other words, if we look at from the mean, which is 7.5 in this case, to 9.4, 34%, 34.13% to be exact, of all the data falls in there. And then from 5.6, 7.3, 34.13. So it's actually 68.26. A little over 2/3 of all the data falls between -1 deviation and +1 deviation. For -2 deviations, +2 deviations, 95% of all the data falls in. And that is the 34% and the 34% from +1 deviation. And then there's a 13.59% from -2 to -1 deviation, and 13.59% from +1 to +2 deviations. When you add all those up, 13.59 plus 34.13 plus 34.13 plus 13.59, you get 95%. In other words, 95% of all the data from a sample or a group will fall between -2 deviations and +2 deviations. And then 99.7% falls between -3 deviations and +3 deviations. And if you look for -2 to -3 deviations, it's only 2.14% of all the data. Same as +2 to +3 deviations, 2.14%. So if we have a group of 1,000 unique points and it's normally distributed, and we'll explain more about normal distribution, how this comes about, you will see 997 of those 1,000 points will fall between -3 and +3 deviations. 950 out of that 1,000, or 95%, fall between -2 and +2 deviations. And then 68% fall between -1 deviation and +1 deviation, or 680 of them. Now, what we need to find out is the z-score. And the z-score is found by looking at your individual data minus the mean divided by the standard deviation. And you'll be given this data. And that basic calculation is my x minus my mu, that little cursive u is actually pronounced mu, x minus u divided by sigma. That's a small sigma in the denominator here. It looks like a cursive small letter O. So, if I was looking at someone, how long it takes someone to recover from a concussion, as this is a big thing going on in a lot of sports right now, how long does it take? We could find out, we give them the data that the average person recovers in 7.5 days, and there's a variation, which is actually standard deviation of 1.9 days. So that's my mu is my average, which is my mean, and then my standard deviation 1.9 days. Now, so we have our mean and our standard deviation, and I want to know what percent among the curve, remember that curve is 100%, where does that fall if someone takes 8 days to recover? I'm going to take my formula from before, remember my mean 7.5, my deviation 1.9, and I'm looking at my sample of 8. So it's 8 minus 7.5, which is my sample minus my mean, which is 0.5, divided by my deviation, which is given to us 1.9. And I get 0.26. It's 0.26 deviations. And you see I've drawn a dotted line here close to the mean. 68% fall between -1 and +1 deviations. So in 8 days, you can see it falls at 0.26 deviations, pretty close to the mean right there, which is not that far from it. And what I've done here, and we'll go over this more in class, but I've written what this would be. 7.5 is the mean, I've written below it. +1 deviation is 7.5 plus 1.9, which is 9.4. 2 deviations, 7.9 plus 1.9 plus 1.9, which is 11.3. And then 3 deviations, 7.5 plus 1.9 plus 1.9 plus 1.9. I go the same direction towards the left. -1 deviation, 7.5 minus 1.9, which is 5.6. 7.5 minus 1.9 minus 1.9 is 3.7, or minus 2 deviations. And then 7.5 minus 1.9 minus 1.9 minus 1.9 minus 3 deviation, 1.8. So in other words, 99.7% of all concussions, people recover between 1.8 and 13.2 days. 68% of all people with concussions, based on this data, recover between 5.6 and 9.4 days. So our individual here at 8 days falls at 0.26 deviations. He falls within 1 deviation here. Now, let's look at another example here. What if a person recovers in 1 day? I'm going to do the same thing as before. I've got a mean of 7.5 days, a deviation 1.9 days. I'm going to subtract my 1 day from my sample here. 1 minus 7.5 is minus 6.5. Divide 1.9, that's negative 3.42. Now, when I look at this, remember 99.7% of all the data falls between -3 and +3 deviations. And negative 3.42 is way less than even my minus 3 deviations of 1.8 days. So it's 1 day. So very unlikely, 0.13%, because 99.7% fall between minus 3 and plus 3 deviations. Very unlikely someone will recover in less than 1 day.